Do you see it, right?
Yes.
So let's start from the question about RNN. Here, I will say that right answers are the first one and the last one. Let's discuss why it is like this. So in the first option, we can say that RNNs are designed to handle sequential data by maintaining a hidden state that captures information from previous time steps, effectively comparing context over sequences. The second option is incorrect because this type of architecture can be applied to a variety of sequence modeling tasks, such as speech recognition, time series prediction, and language translation. It's not only text generation, so it is like this. For the third option, modern LLMs like GPT of third version and BERT use transformer architecture with self-attention mechanism, which have largely represent RNNs due to their efficient and ability to model long-range dependencies. And the last one, recurrent networks often face the vanishing gradient problem during training, making it difficult to learn long-term dependencies in sequences. If we will discuss third question, we will say that first one is right, and this one, and the last one. For the first option, we will say that this is the classic language modeling task where the model learns to predict the next word given the previous words. For the second option, LLMs, language models typically predict feature tokens, not pass ones. If we discuss masked token models like BERT use masked language modeling to predict missing tokens in a sequence. And for the last option, language models can be fine-tuned for classification tasks, such as statement analysis or topic classification. Okay, in the third question, we will say that with fixed query and varying all the key vectors, because the attention mechanism computes scores by comparing the fixed query vector to all key vectors. We discussed it a lot. Question about blue score. I think we had such question in maybe in 3 previous lessons. I don't really remember, but here the right question will be requires the human writing translation. Blue score evaluates machine translation quality by comparing it against one or more reference translations. Here, next question about positional encoding, and here we can say that this one. Why I chose these options, because the first option, positional encoding, injects information about the position of each token, which is essential since transformer lack inert positional awareness. And here, sinusoidal positional encodings enable the model to handle sequences longer than those seen during training by extrapolation positional patterns. And for the last statement, we can say that positional encoding allows models to generalize to longer sequences. Okay, the next question about BERT, and here we will choose this one because BERT utilize the encoder part of the transformer architecture to capture bidirectional context. And that's it. Here, we can say that the right one is second statement, builds informative embeddings for sequences. The first one would be incorrect because BERT produces embeddings for both tokens and entire sequences using CLS token. For the second option, BERT's CLS token embedding represents the entire sequence useful for classification tasks. Here, we say that BERT is not designed for text generation tasks. For example, GPT designed for this. And or transformer in the initial representation. So, and we can't say that BERT specialized for solving mathematical problems. Maybe we will say that large language models can do it, but not BERT. Here, I would say that we can choose first one and third one, because in the first option, BERT is pertained using masked language modeling and text sentence prediction. Here, BERT consists only of the encoder part of the transformer. In the third option, BERT can be fine-tuned for tasks like question answering, text classification, and more. And for the last statement, BERT is not limited to sequence modeling. Let's talk about ELMA. Here I would choose the last question or the last option because the first one would be incorrect because of ELMA relies on LSTM, not self-attention mechanism. ELMA doesn't employ self-attention at any stage. ELMA uses two LSTMs to capture bidirectional context, and this one is the most correct version because ELMA uses separate LSTMs for processing sequence in both forward and backward directions. And in the last question, I would I would choose these options. In the first one, GPT models predict the next token based on previous tokens, processing sequences sequentially. If we will talk about masked language modeling, it's wrong because it would be correct for BERT, but not for GPT, because GPT produces autoregression task, and it's different strategies. And the third option, GPT-2 can generate coherent and contextually relevant text without additional fine-tuning. And in the last one, GPT-2 and newer models are capable of generating realistic and grammatically correct texts. So any questions about our discussion? Maybe something it's not clear right now?
I don't have any questions. Thank you.
Okay, nice. So let's practice a little bit the BERT topic. Today we will delve into the application of BERT. We can, okay, BERT is a short name. We can say that it is bidirectional encoder representations from transformers because of this BERT. And it's a solve text classification task. We will explore the theoretical information of BERT, understand how to load and use pre-trained models, and walk through a practical implementation using code examples. Maybe you will practice a little bit more at home after our discussion and this lesson. Okay, let's start. I want to say in the beginning of the lesson that okay, I want just to tell a little introduction to the BERT architecture. It's a power language representation model developed by Google. It has revolutionized natural language processing by introducing bidirectional training of transformer models, leading to significant improvements in various NLP tasks. And key features of BERT are bidirectional training. Unlike traditional models that read text sequences, BERT reads the entire sequence of words at once, allowing it to understand the context of a word based on all of its I mean that it understand and left and right of the word, all the context which we have. Also, BERT comes with pre-trained models on large corpora like Wikipedia. These models can be fine-tuned for specific tasks. And BERT can be used for a variety of tasks, including text classification, question answering, and name entity recognition. It will change when we will change the last layer of our model, and we will look how does it works. So in the first step, we can load pre-trained BERT model. We will use transformers library by Hugging Face, which provides easy access to pre-trained model and tokenizers. By the way, okay, I will explain you how to use it. Hugging Face, it's a big site, and they usually create more features on it. So by the way, we can firstly you can have account here, and you can use all their models which they have for the for the this year's previous they reached a lot of new types of they loaded a lot of models to their site, and in the beginning of their progress, they had natural language processing models, and we can see it here. But now they have big part of computer vision models and multimodal architectures. You can filter it by push the button. For example, I need a text classification model. I can filter it, and also I can choose languages that I want. For example, I need only Russian model, and here I will have the relevant models for my wishes. So you can search not only for models, you can search for data sets here, and you can find a lot of data sets for your task. Also, you can see here that you can search not only for text data sets. I can choose right now text modality, but there are huge options. For example, it will be not a good example, because here I need access for this repository, but we will find something free for access. And here we can see viewer, dataset viewer, where we can see examples how our dataset will look like, and we can read the entire texts. So you can see card information for this dataset, and you can choose whatever you want. Also, they have really good documentation, and you can search for all the information, because they have really good exploration of a lot of topics. Give me a second. I want show you NLP course, because it's really good. I will show on diffusers example. In image processing, we have diffusers models, and here you can read about them a lot. If you're interested in, I would search for natural language processing course. It is really good, and you can dip a little bit to practice working with their library. I really enjoy it. So if you need it, just let me know, and I will send you in the Telegram in our chat. Okay, right now let's just continue our lesson. As I said, we'll use Transformers library, and they provide pre-trained models and tokenizers. We will use pipeline in the first code block. The simplest way to use a pre-trained model is through a pipeline. It is a high-level interface for various NLP tasks. By the way, not only for natural language processing tasks, and for vision models, they have this function, and for multi-models. Here, we will pass a few masks. The task we want to perform, which predicts masked words in a sentence, and the specific pre-trained model we are using. Here I can run the code, and while pipelines are convent, they are not flexible for tasks like fine-tuning. Therefore, we'll load the model and tokenizer manually for more control. We'll do it here. We will use, you can see the result of our task. We wanted to predict mask token flow IMA something model, and the highest probability was on role, word, fashion, business, modeling. Maybe in this example, it's not the best option, but I think you can use it in many tasks, and you can change here when you will practice it with in home. You can change the model, and you can change the statement. Maybe you will find more better options how to share, how to see the result of the model, so you can play at home with it. Okay, distal BERT. It's here we see that it is tokenizer. Tokenize the input text into tokens that the model can understand. Here it's class of the model. This the pre-trained BERT model without the final classification word. You can, if you're interested in how does it look like these classes, you can go to the source code in Transformers repository, and you can find there would be a lot of different types of the models. You can see their raw code. You can see how does it look like. Maybe you will find something interesting in their repository, because usually how to understand which class we need to import the model. Because if we will use another type of the model, for example, they have multilingual BERT-based uncase, and it's not distilled BERT model class. We can't use it for it. So you can search models here, and when you will see example, okay, it's not the best example. For example, okay, it's a lot of large language models. So let's choose text classification, and not distal BERT, something another one. Usually, yeah, here they write classes of models, how to load it without any issues. And you can find additional information about all you're interested in. They can write it here in the buttons on the beginning of information. And here you can go in through your files. You will have config.json, and here you can see architecture type that you need for load your model, and you can see its vocabulary size, model type, and other parameters of your model. Okay, so let's continue. Here we will tokenize text and generate embeddings. Firstly, we convert text into format suitable for the model. We did it a lot of time. We return tensors, specifics that the tokenizer should return PyTorch tensors. And the last hidden state contains embeddings for each token. So yeah, you can see how does it look like. We can delve deeper into what the tokenizer does and see here. We see here inputs IDs. It's the token IDs corresponding to the input text. Attention mask indicates which tokens should be attended to one and which should be ignored. It's zeros. For example, we will ignore padding tokens, some specific special tokens. And here we can see that we have converts IDs to tokens. It's converts token IDs back to human renewable tokens and decode a function that converts token IDs back to a string. You can see visualization here. How does it works? Maybe it would explain you more clear what is going on in tokenization. Do you have any questions here? Maybe you didn't understand something.
It was pretty clear. Thank you.
Okay, let's move on to preparing the dataset. And we will now load and prepare a dataset for statement classification. Here we can see a little output. How does it look like? It's the Stanford statement tree bank dataset. We have a text column that contains the sentences, and label contains the statement 1 for positive and 0 for negative. For performance performance reasons, we will use only first 2,000 entires. And okay, let's run it. The dataset is relatively balanced between positive and negative statements. We can see it here in the output. Why should we be interested in this factor? Because when we will predict our results and then measure metrics, we need to understand it is classification task, and we need to choose a metric that we will use. And we need to understand in these moments that we can't use accuracy because of its formula, because it would have a lot of leaks if we will use it on disbalance data sets, because if we had in 3 times more positive label than negative, I will not choose accuracy metric. Okay, we need to convert our text, our text data into features that can be used by classifier. we will tokenize that text and handle paddings. We passed 1 second. Okay. Yeah, here I can explain you this. Okay, let's run the code. And here you see that we use flag padding true. So it ensures all the sequences are the same length by padding shorter sequences. And here we have another flag, PET. It means that we will return PyTorch tensors, because you can use not only a PyTorch library, and besides on it, we can return different types of sequences. And also, we can see in this part of the code that, yeah, here, that we have a tensor of size 2000 and 59. And this 59 is the maximum sequence length after padding. And attention mask indicates which tokens are actual data, and we show it in 1, and which are padding are shown to zeros. So we can see how does look our input IDs here. And we can visualize the attention mask. It helps us understand where padding occurs. I think in this visualization would be really clear how does it looks like and how does it works. So if we will go in a little bit next, we see here model the devices. If you have access to GPU, you can speed up computations, and we did it a lot of times. So here we can initialize our device and then move our model to device. But you should be you should have a lot of attention if you moved your model to the device. You need to move all your tensors to this device too. If you will not do it, you will have issue. I think I can demonstrate it to you. Let's run this code, and it would be now without any issues. We see the result. But if I will, for example, not move, okay, just I will demonstrate how does it works if I will move it to CPU. And I will have the error, and usually it looks like this. I saw it a lot of times. And when you see this issue, you usually understand that there's something wrong. You didn't move some tensors to device on which your model is right now. So you need to be careful in this. So let's move on to building and training a classifier. Now we'll extract features using BERT and train a logistic regression classifier. And here 1 second. Okay. I want to check something. Okay, yeah. Here, I want to say you that in this part we had batch processing. We process data in batches, handle memory contains. Because of this, we have batch size here, and also we had last hidden state that show us the output embeddings for all tokens. This slice we use because we select the embeddings for CLS token position 0 for each sequence. And also we compile all batches into a single array, and you can see it in the last row, in the last line of code. Okay, and here we will split our dataset for training and testing sets. We reserve 20% of the data for testing. We will use logistic regression for this. It's a simple yet effective classifier for binary classification tasks. And if I will run it, okay. So in the beginning, we need to initialize logistic regression, and then you can train it. You can train it on training features. You split your dataset for training set and testing set. So here we trained our model, and here we can evaluate the model. We will have this accuracy because the balance of our dataset, we can use accuracy. It's achieved our metric on 85% on the test set. And here we can plot a ROC curve. It's plot the true positive rate against the false positive rate at versus threshold settings. And area under the curve, a measure of the model ability to distinguish between classes. We can then compare it with a dummy classifier. A dummy classifier always predict the most frequent class, achieves around 52% accuracy, but our model significantly outperform the dummy classifier. So we can apply BERT model for a new dataset to see if we can improve upon previous results. Offensive content in the dataset have been censored. for appropriations. And here the dataset contains comments labels as should ban. We can see zeros and ones, and we predict whether a comment should be banned based on its content. We need to handle long sequences appropriately. So we passed let's see how does it looks like. And here we also can when we tokenize our text, we also can use max length of the sequence. I will find where we have it. Yeah, it's a little bit further. So you can see here that we have here max length of the sentence. It's 512. It sets the maximum sequence length for this count of tokens. And here we also have not only padding, we have truncation. We truncate sequences longer than maximum length. And we can then extract features. We process all 1000 samples in batches and extract features. So let's run all the code here. Here, the model achieves an AUK indicating good predictive performance. Our previous model using word embeddings had an average ROC AUK around, let's see. Okay, it's pretty close, I think. And also you can try by yourself use large language larger BERT models like BERT-base uncased or BERT large are uncased. I said it that you can use this type of models in the beginning. And we need to understand classes that we need to import from transformers library to import for load all these models. I can help you a little bit maybe it will be more convenient if I will show you when you will try it at home. So, for example, we interested in use BERT-base uncased. I will search for this model. So it will looks like something like this. And now we can return to our notebook. We can import from transformers library classes for this model. Let's see how we can use it. Here they had information about classes that we need to use for this model, but maybe also you can see it here in the files, as we saw in the beginning of the lesson. And also you have here class for import. Let's just try their option. Let's copy paste it here. And also we can move this model to our device in the beginning to not to do this work further. Okay, maybe if I will use this, it will help. They just say that that class haven't got moving to the device, and because of this, I tried to use another class for BERT models. I just know that this model works with this class, but also if you are not sure in choosing class for your model to import it, you can usually import model and tokenizer with auto model class and auto tokenizer. You can see it on their documentations. How does it look like? But usually it works like a function in the raw code, which see a configuration of your model, each architecture, and try to connect it with class of all the models that they have. So when you will use this model, you need fine-tune involves updating the weights of the BERT model during training to improve performance specific task. And you will prepare data loaders, create PyTorch data loaders for training and validation data. You will add classification layer on the top of the BERT, define loss function, and optimizer. Usually you can use cross entropy loss and Adam V optimizer. And then you need to evaluate on the model, on the validation set after each epoch. So here you can practice more. If you will have any issues, I can help you to find. Let's just 1 second. I will search for NLP Hugging Face course. Yeah, if you will have any problems while you will train your BERT model, you can see information here. Firstly, you will read more about their BERT models on their library. And also here they had yeah, using transformers, models, tokenizers, fine-tuning. Yeah. Give me a second. I will search the part that they have example of training their models. let's go through. Okay, so here they explain pipelines that we saw in the beginning of the lesson. And then yeah, here they explain how to train their models. Also, you can tokenize functions as they show in the functions, and then via map tokenize it in a multi-processing way. Also, you can do it in a data loader, for example. When you will, you can just write code of the data set and then convert it from the data loader. Also, they will show you yeah, how does what model returns, and here you can find training loop. So we did it a lot of times on this on the lessons, but here you will have the example. So you need initialize your model in the beginning, then move it to device. Then this line of code will move your model to the training process. You will not skip dropouts, batch normalizations, for example, and your model will be ready for training. You will have gradients. You not use with torch no grad. So here gradients are going through your models on the backward steps. And on each batch, you move all the tensors to your device. Here you can get logits. We saw in the beginning of this site window. So we saw what model have in the output, the loss function and logits. So here you use loss output, and you can use backward to you did here forward step, and here you use backward. Then as we did a lot of times, optimizer step, linear scheduler, you can use it too. It will mention learning rate value while you're training. Also, you do optimizer zero grad, and that's it. So here they also has the evaluation loop. How does it need to look like? And here we see with storage no grad. That means that our gradients are not going through our model. And also we did a model point eval to make sure that our model will not use dropout, because if I will see what is in my model, I can see dropouts on some parts of the model. And also you can see dimensions of your matrices. For example, this embedding layer, and you can see here what is in your declinator. So you can mention that your declinator has vocabulary size of the same value, what is on the x dimension of embedding lawyer. And I told you a lot of times that it connect with each other. Also, you can see dimensions of self-attention lawyers. You can see how looks query metrics. You see that it has a dimension of hidden size of BERT model. And also on the output, we have linear lawyer with number of the features that we want on the output. So we can choose lawyer that we need to in our specific task. For example, if we will have a classification task and we have only 2 classes, we will change a last lawyer to in features with dimension size that we have, and out features would be 2 because we have only 2 classes, 0 or 1. And you can use it and train as you want. I mean, fine tune. Do you have any questions? I think that I told you all the information that I had for this lesson. If you're interested in something else, let me know for this 1 or 2 minutes. But if you not have questions, I wish you a good evening.
Thank you. Bye.
Okay, thank you so much for your attention. Have a nice evening and week. Goodbye.